And I wanted to look at this last one. This last one was causing more trouble than the others, so I wanted to just work on this one a little bit, just to see maybe if I could point out maybe where you were making a mistake. So let's do that. All right, so what's going on here is we're asked to find a line integral through a vector field. So we know that what vector functions give curves, right? Vector functions give curves. We said it many times. So this is a curve in three-dimensional space, like this. And maybe, t equals 0 is here, and t equals 1 is here. And so our path then is starting at t equals 0 to t equals 1. That's our path C. And then this curve is through a vector field, right? So there's vectors everywhere. Every location has a vector according to this vector field. And so it's a path through a vector field. And so starting at t equals 0, we're going to accumulate the vectors along the path dot a little displacement along the path. What's a dr? Dr is it's like a little vector quantity showing a little displacement along the path. And when you do f dot dr, then it's like you accumulate if this is a force field, say, this is a force field and a path through a force field, it's like you're accumulating all the little bits of work. So this gives a little bit of work, d work. And then we're going to accumulate all that work starting at 0 to 1. And this is the work that the force field does on the object as it travels that path. Okay, so that's kind of what's going on when you're asked to solve this problem. That's kind of the concept of what's going on. And then there's the algebra side to it. So let's work on the algebra side. So we're going to rewrite f in terms of x, y, z on the path, right? So here's our x, y, z points on the path. So if we rewrite f, it'll be 5 times sine of x, which is t to the 6th, negative 3 cosine of negative t to the 5th, and then negative 2xz, which would be t to the 6th, t to the 4th. Can I just write t to the 10th? So how are we? Is we good so far? So what? That's the force field or the vector field, but written in terms of t, which is x, y, and z. And then dot dr. So dr will be the rate of change times dt. So the rate of change will be 6t to the 5th, negative 5t to the 4th, and 4t cubed dt. So follow that so far. Any questions or mistakes? If you catch a mistake, if I ever make a mistake, please speak up right away. So I rewrote the force field in terms of t. Took the derivative of the path, right? Of the vector function. That's my dr times dt. And now we're going to execute the dot product, which will be 30 t to the 5th sine t to the 6th plus 15 t to the 4th cosine negative t to the 5th plus negative 8 t to the 13th. All right, again, if you catch a mistake, please speak up. But that's probably, there's lots of chances for mistakes here. That's probably why the success was a little bit lower on this one. It's more difficult to not make any mistakes along the way here. And that's going to be t goes from 0 to 1. So any questions so far? So what you have here then is you have two u substitution antiderivatives. I'm going to try to do those without u substitution. So kind of noticing that this is just the result of the chain rule. trying to like reverse the chain rule here, because this t to the fifth is the derivative of t to the sixth, right? So that's like chain rules. I'm going to try to reverse that. So if I reverse that, I'm going to have what? Negative cosine t to the sixth, because the derivative of negative cosine is positive sine. And I'm going to have this 30. And then taking the derivative, I've had 6t to the fifth, but I don't have the 6, so I'm going to have 1/6. So that's kind of seeing that as the result of chain rule and trying to recover the original function that would give that derivative. Okay, same thing here. So I'm going to have negative sine. So the antiderivative is going to be sine. And if you need to use u substitution, that's perfectly fine. So the antiderivative of cosine is negative sine, but I'm going to get that negative when I do the derivative of the inside there. So I think I can just do plus here, 15, and then 1/5 for the t to the fifth. So now if I do the derivative of this, now I'm going to need a negative, right? Because if I do the derivative, I get positive cosine, and then times negative 5t to the fourth. So I'm going to need a negative. So subtract. Okay, and then finally we're going to have negative 8/14 t to the 14th. And that's going to be from 0 to 1. Now, here's another potential for mistake. Plugging 0 into this does not give 0. Why? Cosine. Plugging 0 into cosine does not give 0. Cosine of 0 is 1. Okay? So, plug 1 in, but you gotta evaluate 0 plugged in. It doesn't always, it gives 0 here on sine, it gives 0 on t to the 14th, but 0 in here does not give 0. So that might be another place where we got tripped up.
Professor, when you erased, did your 15 turn into a 5?
I
think right after the plus sign that you put in the minus from the chain rule for the middle term. It's like right in the middle of the bottom line.
Oh, here?
Yeah.
Thank you. Thank you very much. Yes, that's 15 should be 15. Thank you. Okay, other questions, comments? So I'll let you take it from there. So, you got some little bit more difficult antiderivatives. If you need u sub, use u sub, but then also watch out, cosine of 0 is not 0. Any other questions on this one? Okay, so we're going to do more line integrals today, and hopefully we get the hang of it. But then we're going to use these line integrals to kind of advance the conversation a little bit. Can I erase? Okay, here we go. So I want to take a look at let's see. These two. That's a white space here. Okay. So I'm going to look at, so I've got two vector fields. This first one is negative 2y. So this is F1. And we'll call that F1. And then F2 is negative 2x. And I'm showing those vector fields with these gray vectors. Do those gray vectors show up? Can you see those gray vectors?
Yes.
Easy to see? Okay, good. And then we're going to take the same two paths in those vector fields and compute the line integral. So these are special paths because they make a loop. They're a circuit or a loop. So they start, wherever you start, you go around the circuit and then you end up where you started. And so that's called a circulation line integral. Circulation. So circulation means that the path Path is a closed circuit or closed loop. You end up where you started. Okay, so these are two separate circulation line integrals. I got a triangle circulation and a circular circulation. Okay, there was a question.
So I was just trying to ask. So is this what? Because in physics they talk about like closed loop integrals. Is this what that is?
Yeah, path. Yeah, closed loop. So we're going to call it a circulation line integral. So the path is a closed loop.
Okay, thank you.
Yep. And so then the notation is, so we'll still do our line integral through a vector field, but we'll put a circle on the integral sign, and that means that the path that we're doing is going to be a closed loop or a closed circuit. Okay, so we're going to do 4 of these. And we're going to do, for the same 2 paths through 2 different vector fields, we're going to calculate 4 circulation line integrals. So the first thing we need to do is parameterize our paths. So I'm going to use this as going to be T for triangle, and then C for circle. And so we'll start with the triangle. And what is it going to take to parameterize this triangular path? What's that going to be like doing that in general? So what will our overall approach be when it comes to parameterizing the triangular loop?
Could we set y equal to t?
And then will that be true for the whole way?
Would we have to separate it into 3 integrals?
Yeah, so the path, well, yeah, 3 pieces, right? So the path T has to be 3. These are 3 totally independent pieces. The only thing that's in common are the endpoints. But there's nothing about this path that, it's a totally different path, exclusive from this one, exclusive from this one. So to get T, it's going to be, you're going to have a T1, a T2, and a T3. So we're going to start, let's start down here. And so T is going to consist of a T1, T2, and T3. So T is the union of T1, T2, and T3. That's what T consists of. Okay, so T1 first. So we're going to write a vector function for T1. So we could call that, say, R of T1, T. And what will that be? So, and we're going to start down here and go up to here, like this direction. And so remember that parameterization is just all points on the path, right? So it's just defining all ordered pairs, all points on the path. So, what can we say about all points on that path?
Their x is all -1.
Yeah, no matter what point you have, the x is -1. It's a vertical line. So we can just write down that x is -1, because that's true for every point on this path. The parameterization of a path is defining the whole curve. It's defining the points on the curve, right? And so x is always -1, and then y is what varies, right? Y varies from here to here, and so then we can just make yt, and we know that y will vary with, or y will vary with t. Okay, what about t2? So defining our t2. What can we say about t2? That's the top path.
Y is just 1.
Y is 1, always. And then again, we can just let x vary with t. Okay, finally, T3. So now T3, is not as simple, right? These were greatly simplified by the fact that you had a constant value for one of your components, right? So you had x was -1, y was +1. So for T3, which is coming down this way, this is just a general line segment. I'm going to give you a technique for doing a general line segment, which goes back to our vector equation of a line. Remember when back in the first week of class, back in the very first week of class, we learned the equation of a line, and then later we said, oh, that was just an example of a vector function, right? When we got to vector functions, we said, oh, we already did one type of vector function. That was our line equation. So what was that? So that was all points x, y equal, and we did it in R3, but we can just do a two-dimensional version of it. And so here's what I want to, so to do this, so you can pick any point on the line and then any vector parallel to the line, like we've said before. But here's a nice technique. Choose your point to be your starting point, and then choose your parallel vector to be a vector that just is the whole segment, right? So the vector whose tail is at the starting point and whose tip is at the ending point. So this is just one way to do this, but I'll show you the advantage in a second. So what vector would that be? Entire segment. Okay, so this isn't required, but it's just a nice way to do this. So now down here T3, what would the starting point be in our case?
1, 1.
1, 1. So now I'm doing RT3 of t, and that's going to be 1, 1. And we're going to do plus t times, and then what's the vector whose tail is at the starting point and tip at the ending point? What vector is that?
-2, -2.
He wants -2, -2. The rest of you agree with that? Remember, the vector is the changes, right? So how much does x change from here to here? How much does y change from there to there?
-2.
Yeah, -2, -2 both. Or you can take the coordinates of the tip and subtract the coordinates of the tail, which gives you the same thing. So what we get then for T3 is 1 minus 2t, 1 minus 2t. Did I make it? Can you see the whole thing? And now so here's the advantage to taking this strategy, is that if t equals 0 will be your starting point of the segment, and then t equals 1 will be the ending point. And let's try that. So if t equals 0, what point do we get? Down here? We get 1, 1. See that? That's our starting point. If we put t equals 1 in, you get 1 minus 2, 1 minus 2, -1, -1. It's our final point. So if you ever parameterize a segment this way, then your integral will always be from 0 to 1. You never have to figure out what the t values are. It'll always be from 0 to 1. Okay, so we got the t path all parameterized. It's going to be -1t, and then t1, and then 1 minus 2t, 1 minus 2t. All right, what about c? So that's going to be only one piece. It's a circle. So what do we think for R of c? And let's say we'll start here at the right side and go counterclockwise. How can we parameterize a circle starting here and going counterclockwise around?
Cosine t, sine t.
Yeah, definitely want to use the when we talked about this when we were learning vector functions. The natural way to parameterize circles and ellipses is with cosine and sine. If you don't use cosine and sine, it's clunky. It's got pluses and minuses. It's got square roots. But cosine and sine are by very definition are points on the circle, right? The x-coordinate on the unit circle by definition is cosine. The y-coordinate on the unit circle by definition is sine. So let's use them. And that makes for a nice, much more natural way to parameterize a circle. So we got both paths. We got our t path, which is 3 pieces, 3 segments, and then we got the c path, which is the whole circle. Questions on parameterizing the paths? Okay, so now it's time to set up these integrals. So we're gonna do the circulation of path T and path C through F1, and then the circulation of T and C through path 2. So we'll do path 1 first, or sorry, field 1 and field 2. So we'll do field 1 first. So F1 is our negative 2y, and we're gonna do for t, the circulation over t. So what will computing this line integral look like then for the triangular circulation integral? Just in general, what will that calculation look like?
F of r over of t times the magnitude of rt.
Okay, so you're getting into the inside. I'm more talking about the overall structure of the answers before we get to the actual integral.
Would we need 3 integrals for each segment, or 1 integral for each segment?
Yeah, so we're gonna have to add the line integral for t1 plus the line integral for t2 plus the line integral for t3. And that will be once we do those 3, then it'll be the circulation around t. That will be the circulation. Okay, so here we go. So f dot dr for t1. So what will f be? So our field is negative 2y, but along path t1, that will be negative 2 and t, right? The y coordinate on path 1 is always t. So that's rewriting the vector field in terms of our parameterization of the curve. And then dot dr. What's dr for this?
1.
I think
0, 1.
0, 1. And that from what to what? So t goes from what to what?
Negative 1 to
Yeah, it'll be negative 1 to 1 because t is the same as y. So we're just going to do the y coordinate is the same as t, so negative 1 to 1. All right, next one. Our f, again, negative 2y. What will that be for t2? Negative 2 comma
1.
1, because y now is 1. Dot dr, which is
0, 1.
1, 0.
1, 0. And that from what to what? So t goes from,
Negative 1 to 1.
and then finally t3. So f is negative 2 and what?
Sine t.
Oh. 1 minus 2.
1. Here's y. Here's y for t3, 1 minus 2t.
Sorry, right. 1 minus 2t.
Yep. Dot dr. What's dr?
Negative 2, negative 2.
Derivatives, right? Derivative of each dt. And this t is from what to what? What do we say?
0 to
Yeah, because of the way I showed you how to do it, it'll always, a segment like that will always be from 0 to 1. If you make the starting point be that point, and then make the vector for the entire line segment as your parallel vector, then your t will always go from 0 to 1. All right, so we can actually, because these have the same bounds, the first two vectors have the same bound, or two integrals have the same bounds, I want to combine these and then leave this one separate, and then we'll let the software do the rest. So this will be from -1 to 1. So dot product here is t, right? Dot product here is -2, I think. Agree? So we can do t minus 2 dt. That combines the first two integrals. Dot product is t, dot product is -2. Plus that last integral is 0 to 1. It looks like 4 minus 2 plus 4t. So I'm going to leave it like that, and I'm going to let my software do. But let's look at that and let's maybe predict what do we think that might be. So looking at the vector field and the path. So what about this first along T1?
Probably 0.
Yeah, it looks like there's symmetry, right? So whatever, this is a negative contribution down here, but then this is positive, but it looks like symmetric. So along T1 is 0. What about along T2?
Negative.
Negative. We're going against all the vectors, right? All the vectors are pointing the opposite direction. So we expect a negative value for T2. What about T3?
Positive.
Yeah, so it's just a little bit positive here, and then gets more and more positive as we go towards the end of the path. So this is kind of like jury's out, right? We got 0, negative, positive, and there's no way to tell which will be bigger, the negative contribution or the positive. So in terms of predicting what the value of this circulation is, it could be negative, it could be positive, it could be 0. So don't know. Hard to predict just by looking at the picture.
How did you get the integral you boxed it?
I simplified this.
By hand or oh?
Yeah, because this dot product was just t. This dot product was just -2. So these have the same bounds, so I combined it, t minus 2.
Oh, thank you.
Yeah, sure. And then I just simplified, I did the dot product and simplified it. Okay, now the same, let's do C. It'll be a little faster. So I'm going to erase here, and we'll do C through this same vector field F1. So I trust you have that written down. I do too. I have it written down, so okay. So now we're going to do C. In vector field 1. So what do we got? So we're going to go around the circulation line integral. And so here we go. F is still -2y. And then what about for C? -2 comma
Sine t.
sine t dot dr negative sine positive cosine dt. Are we good? And do the dot product, and you're going to get, looks like +2 sine t plus sine t cosine t dt. What will our bounds be for this? T will go from what to what?
0 to 2 pi.
Yeah, so t is our argument in the sine and cosine, so it's angle measure. So it'll go from 0 to 2 pi. Okay, and then let's predict this one before we find out what the value is. So let's look across the top here. So at the beginning here, first quadrant looks what, positive or negative?
Positive.
Positive. What about second quadrant?
Kind of closer to 0, but still kind of positive.
Yeah. So we got still positive up here, and then maybe towards the very it gets like zero-ish down at the end, close to angle pi. But yeah, positive, zero-ish. Okay, what about coming down the bottom around the bottom half?
Like 0 is to negative.
Yeah, so zero-ish, but then negative and getting more kind of stronger negative. But you see that there's kind of a symmetry to this field over the x-axis, so it looks like the positive contribution in the first half of the revolution is going to be equal to the negative contribution coming back. Does everyone see that? So we think this is going to be 0. Questions on, so then once we get all 4 written out, then we're going to actually get the values for the 4 circulation line integrals. But we'll move on to the other field now. Okay? Any questions on the first 2? All right, here we go. So now we're going to do F2. Let's get that going here. So let's do this. Oh, it's in here. Okay, so now F2 is negative 2 comma x. We're using the same parameterized curves, T and C. And so this will go a little faster, I think. So for T, F2, the circulation around T, F2.dr will again be the sum of T1 plus T2 plus T3. All right, so here we go. F2 is negative 2x. So for T1, what is negative 2x?
Negative 2, negative 1.
Right. Dot dr?
0, 1.
0, 1. And that from what to what?
Negative 1, 1.
Yeah, that's our y. Y value is t. Again, same path, negative 1 to 1. And then x also goes from negative 1 to 1, right? In the second, in T2 here. Negative 2 and x, which is?
T.
T. dr is?
1, 0.
Okay, so there's our the T1 line integral, and then the T2 line integral, and then the T3 is 0 to 1, negative 2x, which is negative 2.
1 minus 2t.
This one actually turns out to be the exact same T3 integral as the other because our x and y are the same. So dr, again, is negative 2 dt. Again, I'm going to combine, I'm going to do the dot product. So this dot product is, what, negative 1. This dot product is negative 2. So I'll have from negative 1 to 1 of negative 3 dt plus the same as last time, which was 4 minus, or plus 2, minus 2, sorry. Minus 2 minus 4t.
It was plus 40.
What's that?
It was plus 40.
Plus 14?
Yes.
Okay, thank you. I agree. Okay, let's try to predict this one. So now we're looking here. What do we got? Coming up T1. What we expect that integral to be?
That'll be negative.
Negative. T2.
Negative.
Negative. So T3.
A little bit positive.
Little bit positive, right? It's kind of zero-ish at the beginning because the vectors are orthogonal. A little teeny bit positive at the beginning and then more positive at the end. But we had all this negative coming up T1, all this negative coming across T2, and then some positive on T3. Conclusion?
Probably negative.
Yeah, probably negative. We're going to go that's going to be less than 0. Okay, last one. That's the circular path through F2. So C, that's going to be our circulation F2 dr, and that's going to be equal to integral negative 2x for path C, negative 2
Cosine.
cosine
Cosine
t dr is
negative sine of t cosine t.
I didn't leave myself enough room here. So I think we don't need path T anymore, so I'm going to give myself some more room. Looks like 2 sine t, but then this time plus cosine squared. And t goes from
0 to 2 pi.
0 to 2 pi again. All right, let's predict. So starting here. What do we say here, first quadrant? Positive, negative, or 0?
Positive.
Positive. Second quadrant?
Positive.
Positive. Third quadrant?
Negative.
A little bit negative.
Little bit negative, right? So it's like zero-ish, and then negative at the bottom, and then fourth quadrant,
A little bit negative.
little bit negative, and zero-ish. So overall net result,
Positive.
Positive.
yeah, this top is really strong positive. These vectors are, lots of them seem almost parallel to the path, and the whole way positive. Then we got some zero-ish, and then kind of just a little part negative toward the bottom. So we're thinking this is going to be positive. Okay, now let's find out the values. So I trust that you can do those Calc 1 and Calc 2, cosine squared, that was Calc 2. But you can do those integrals. Remember, just briefly, how do you do the integral of cosine squared? Does anyone remember?
I use like a trig identity.
Yeah, it's the half angle identity. Cosine squared equals 1/2 1 plus cosine 2t. And sine equals 1/2 1 minus cosine of 2t. So that's called the half angle identity. All right, so I think I can erase everything here. Don't need anything left here. And so here is those 4 integrals that we had. And we're going to find out the values now. So in the first vector field, let's show that. Let's show both of them here. All right. Uh-oh. Okay. In the first vector field, So we said that we predicted, so here's that around C, we predicted that would be 0, and it is indeed 0. The software is doing some numerical method and returning 5.8 times 10 to the minus 16th. So because of the numerical method it's using, it's getting a minuscule error, right? And showing us that like infinitesimal error, basically. So this is 0. Okay, and then we said we weren't sure about this triangular because we had the 0, and then we had the negative, and we had the positive. Well, it turns out when we do that integral, it is indeed 0. So both of these circulation integrals in this vector field negative 2y are 0. Okay, what about the others? So we predicted, I think, positive for one and negative for the other. Let's take a look. So here's through negative 2x. We predicted positive for the circle, and we got pi. So when you actually do the math on that one, you get pi, greater than 0. We were right. And we thought that this triangle was negative, remember? Because we had a strong negative, and then just kind of some moderate positive. And indeed, it's negative 2 when you do that one. Okay, so what's going on here? So notice that in this field, we got our circulation integrals were 0. And so if we think about this as work, like so we're going to drive our car through a wind field or something like that, and we think about these integrals calculating work, the net work is 0. What does that mean? It means that the contribution, the work that the wind does on the car is equal to and opposite the amount of work that the car does on the field in traveling the whole path. So in this first part of the path, this is the wind pushing on the car, right? As the car travels this curve, the wind is pushing on the car, and the wind is doing work. When the car is going against the wind, then the car is doing work on the wind field. The car is pushing back against the wind field, and then we get a negative amount of work. So the net work is 0. That's what we showed by calculating these circulations as 0. And so what we have is this is the idea of conservation of energy. Right? The work that the car put into the field is equal and opposite to the work that the field did on the car, or the wind pushed on the car. So you have conservation of energy. It cancels out, right? It's conserved. Energy is conserved. And so that's what happened with the triangular path as well. And in fact, any path, any circulation integral through this field, so it could be like a peanut shape, like over here in the second quadrant. If you calculated the circulation around this closed loop, for every closed loop, so the circulation in this field is always 0 because you'll always have conservation of energy. But in this one, we showed 2 examples where the net work was not at 0. Going around counterclockwise, we had actually the field did positive work on the car for the whole trip. And going around the triangle, clockwise, the car did work on the field, right? Because we had a negative value. So the car did work on the field, which was not balanced out by the amount of work that the field did on the car. So we got a negative and a positive. So energy not conserved. So Question, important question. So this is called a conservative vector field, because you have conservation of energy for every circulation integral. Every closed loop results in a network of 0. Here, if you can find one loop where the network is not 0, then it's not conservative. The vector field is not conservative. But this vector field is conservative. So, did anyone recognize what is it that makes a vector field conservative? What's special about this vector field that's not true about this vector field? Anyone notice?
Are we talking about the DP diagram?
About what?
Never mind. It was the physics class.
Okay. Oh, that's physics. All right. So there's this. Anyone see what's special about this vector field that's conservative versus this one? It's not conservative.
Isn't the left one a gradient field?
Okay, someone said it.
Is the left one a gradient field?
So he's asking, is this one a gradient field or this one is not? So remember gradient fields. Gradient fields have a potential function. They have a function whose gradient is the field. Can we write a function that has this as its gradient? What is that function?
Like negative 2x plus 1/2 y squared plus c.
Okay, so he wants negative 2. Let's give this some more room here. Negative 2x plus 1/2 y squared plus c. Is the gradient of that function negative 2y? If you took the gradient of that multivariable function, would you get negative 2 and y?
Yeah.
Yes, you would, right? That field that I gave you was a gradient field. In a gradient field, you have conservation of energy, so it's also called a conservative vector field. Gradient fields are conservative. You get conservation of energy, and that means that every closed loop, every circulation integral in a conservative vector field or in a gradient field is equal to 0. We didn't prove it. We just showed 2 examples, right? We just did 2 examples and got 0 for both. So that's not a proof, but I'm just they were examples. But any, like I said, any circulation, any path you take that's a closed loop, if you evaluate the line integral, it will be 0. Okay, what about over here? Is it a gradient field?
No.
Not a gradient field. You can't find there is no function fxy such that that's the gradient of it. Can't do it. So therefore, if it's not a gradient field, it's not conservative. You'll be able to find loops that don't result in a 0 line integral, like we found 2 of them. So, big takeaway, gradient fields are conservative, and that means that every closed loop in a gradient field will have a circulation value of 0. If it's not conservative, it's not a gradient field, then the field is not conservative, and you'll be able to find there will be closed loops that don't give a 0 circulation. Now, you might be able to find some loops that do give 0 circulation, but not all of them will be.